Okay, we're moving on to the back of the Electrochem practice test. Again, we have an overall reaction where they give us the overall voltage and they give us one of the voltages. But the other one they're asking us about is actually the guy being oxidized, and they want his standard reduction potential. So the E0 cell is negative 0.65 volts. They give that to us. They give us the reduction of the copper, 0.34 volts, and the copper is being reduced in our reaction, so I'm going to keep that as 0.34 volts. But then they want the reduction potential for the palladium, which is really the backwards reaction for the palladium. So I wrote it this way. I took the overall, negative 0.65, the reduction of the copper, 0.34, and then instead of adding it to x, I did minus x, because then the x is the reduction potential they want. By putting a minus sign there, I'm saying that if I take the reduction and flip the sign on it, it'll be the oxidation of palladium added to my reduction of copper to equal my overall. So that actually makes sense. That's a little sign thing there. The answer is the 0.99 volts. Okay. For number 9, we have a Nernst equation, different molarities, right? So let's see. Here's our Nernst equation. It's nice to notice that it is at 298 Kelvin, so it is at 25 Celsius, so we are allowed to use this version of it. We do not have to use the more complicated version with the temperatures. The Q expression is going to be a little bit complicated. Products over reactants raised to their coefficients. Only the solid aluminum is not going to be included. All the others are ions, and they're all aqueous, so they're all included. The tin 2 is cubed, the aluminum is squared, the tin 4 is cubed. Okay, this is my Q expression with the numbers plugged in. This will go right there. I'll take the log of it. I'll times it by negative 0.0592 over 6. Let's see, yep, 6 moles of electrons are definitely moving. That's easiest to see with the aluminum, 0 up to positive 3, and there's 2 of them. Okay, so I'm going to put Q there, take the log of it, times it by negative that guy over 6. Add it to the 1.81, which will go right there, and we'll get the answer, which happens to be this. E, 1.93 volts. Okay. For number 10, anode, cathode, An-ox, red cat. So if they want the anode, they want the reduction. Now, what could possibly happen with Ki? Oops. The K has a +1 charge, the I has a -1 charge in the compound Ki. The K cannot get more positive, the I cannot get more negative. All that can happen is that this bond is broken and they're forced to be in their elemental states. So the iodine from -1 up to 0, that's oxidation, so that's happening at the anode. Anode, so it's that guy is produced there. The next question is very similar, except when a group 1 metal is produced in water, it doesn't just sink to the bottom. For the lithium bromide, same deal. The lithium reduced from +1 down to 0, and the bromine is going to be oxidized from -1 to 0. That's oxidation because this charge goes up. Bromine's fine. The bromine is produced at the anode. An-ox. Okay, got this guy at the anode. And he's liquid. Remember, bromine's the only non-metal liquid at room temperature. I want to say that solid lithium is produced at the cathode. But solid lithium will rapidly react with water because it's a group 1 metal. It will do a single replacement where it kicks the hydrogen out, bonds to the hydroxide, that hydrogen is kicked out, this is not balanced, not that it matters, and this hydrogen gas is actually produced at the cathode. So it's actually E. And that is what would happen in the previous question too, but they didn't ask about the cathode. Okay. For number 12, we have a conversion. We've done these in class. It's good to write the reaction. They describe it. Copper 2 ions are being plated into solid copper, so it's got to be down to 0. Electroplating always involves getting the metal down to a 0 neutral solid. And so we start with our grams of copper. Here's the molar mass of copper upside down. I can tell from the description that it's 2 moles of electrons to every mole of copper. Faraday's constant tells me coulombs per mole of electrons. They must have said 2 amps. Yep, 2 amps. 2 amperes is 2 coulombs per second. And everything cancels except for the seconds. You end up with 2,065 seconds, which is 2,070 seconds rounded to 3 sig figs. I'm feeling like they're not holding this number to the correct number of sig figs, but whatever. This doesn't matter. The 2 moles for every mole of copper, that's like an absolute. 13 is similar, but it's backwards. You start with the time aspect, and then you're going to work through Faraday's constant to get from time and coulombs to your grams and such. Silver being reduced only takes 1 mole of electrons. So start with this huge amount of time. There's 60 minutes an hour, 60 seconds in a minute, and they had 6.0 amps, so 6.0 coulombs per second. So the amps get me from time into coulombs. Faraday's constant gets me from coulombs to moles of electrons. The relationship, thinking about it, gets me to moles of my silver. Molar mass of silver, I calculated 36.2 grams, but of course we actually are limited to 2 sig figs. 36 grams of silver. Okay. 14 and 15, these are just interesting. Just something to look up. This is how we mine, when we dig up aluminum, it's in this form, Na3AlF6. It's a big old messy thing. This is why it's a really good idea to recycle aluminum, aluminum foil. It takes a lot of energy to get aluminum out of this compound. So recycling is good, and this is how we used to do it, and that was not nearly as efficient. So don't worry about these two, but that's interesting to know. You might see this, Na3AlF6. Okay, 16. Acidic conditions, the bromate ion is reduced to the bromide ion. Write the balanced half reaction. You don't have to do much figuring out, you just have to find all the mistakes here. So, the first one looks pretty good. That is bromate. IO3 minus is iodate, by the way. I'll zoom in here a little. Okay. It looks like reduction because I'm gaining electrons. That's important. There should be a little negative sign on all the electrons. That's the bromide ion. That looks like it's an acidic solution. This looks like the right answer. Now, what about the other ones? This is messed up. Br2 minus. Is that diatomic bromine? Is it the bromide ion? I can't decide. Also, if you're losing electrons, you're oxidation, not reduction, and we want reduction. Same deal here. Losing electrons. These are oxidations, so they're messed up. And this one has the weird bromide ion. And we also know that we don't balance our oxygens with molecular oxygen. We balance our oxygens with water molecules, and then we balance our hydrogens with H+ ions. Okay, let's balance this guy in acidic solution. Okay, I've got them here. Nitrogens are balanced, bromines are balanced. Balance oxygens with water molecules, plus 3 waters. Balance hydrogens with hydrogen ions, plus 4 H pluses here, and 6 H pluses for this guy. Balance charge. There is, can that be true? There's no charge going on here? All the charge is hidden? Yep, all the charge is hidden here. So I just need to add 4 electrons on the right. Okay, for this guy, -1, -1, positive 6. 6 electrons on the left. 4 and 6 can both go into 12. Let's triple that one and double that one. What do we end up getting here? Okay, this says that the answer to 17 is E. That looks right to me, with the doubling of the bromates, doubling of those, tripling of the nitrogens, doubling of the bromines. 2 times 3 would be 6 waters. There's the 6 waters. And it's in acidic solution, so I don't need to worry about adding hydroxides to both sides. Okay. For 18, which one is not a redox? Well, the ones that definitely are redox are the ones where the charge obviously changes. If you have any pure elements with charges of 0, and they're also bonded, but they're 0, one side they're bonded, another side they're 0, they're definitely redox. So this is definitely a redox. This is definitely a redox. Single replacement, this is 0, this is 0. It's definitely a redox. Generally, most synthesis and decomps are redox. All single replacements are redox, and double replacements are not redox. This guy has the oxygen 0. The oxygen here is oxidized. The chlorine is what ends up being reduced. But it's that pure element by itself that really tells me it's a giveaway that it's absolutely redox. And then I don't have to check more charges. Let's look at this guy. This guy turns out to be the answer. So he is a redox. It's sort of hard to tell, so let's make sure. 2 hydrogens that are each positive 1. 3 oxygens that are each -2. This has to add up to 0. Looks to me like this carbon has to have a positive 4 charge. Let's see, 4, 5, 6, positive 8. Yep, this carbon has to have a positive 4 charge. In water, oxygen's got the -2 charge that he wants to have, and each hydrogen has the positive 1 charge that he wants to have. That works out, that adds up to 0. In carbon dioxide, let's give each of these oxygens the -2 charge they want, so that if this adds up to 0, the carbon has to be, ding, 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 positive 4. So the carbon does not change, he's positive 4. Every oxygen is -2, and every hydrogen is positive 1. So this is not a redox. If one of the choices had been a double replacement, that would be the giveaway. The double replacement would definitely not be redox, because they tend to have charges, trade dancing partners, still keeping the same charges. Okay, happy studying. The only thing that wasn't on this was Gibbs free energy. So also study the Gibbs free energy equation, delta G naught equals -N Faraday's E naught.